Sweet and Parker showed the velocity at which the magnetic field are convected into the reconnecting region are much faster, so that the time scale associated with this velocity are much shorter than the time scales we estimate in our earlier lecture using the diffusion time scale. So now let us have a careful look on how this Sweet and Parker model is working. So we have the neutral sheets and the magnetic field lines are of opposite directions are above and below the neutral sheets. And Sweet and Parker consider a coordinate system where your x-axis is parallel to the magnetic field and it is along the neutral sheet, and y-axis is normal to the neutral sheet. And this configuration doesn't depend on your z coordinates, so the whole problem can be treated as a two-dimensional problem. So in this configuration, they considered a closed loop, a closed rectangular loop with a length L and capital L and your width a small l, and the width is typically the thickness of your reconnecting region or the neutral sheet. So, and this capital L is much larger than your small l. Now, the plasma the magnetic field is convected into this reconnecting region at a velocity v, and the reconnection happens at the neutral sheet, and the energy dumped or dumped into the particle, and the particles are ejected out of the neutral sheet at a velocity vx along the x direction. So with this configuration, let us try to find out what is the velocity at which your magnetic fields are convected into the neutral sheet. This is a Sweet and Parker configuration. So, and this is the closed loop. So let us start with the Stokes theorem, which says the surface integral over curl of B dot ds is equal to line integral of B dot dl. Now the Maxwell's equation says my curl of B is equal to 4 pi by C into J, the current density. So plugging it here, so what am I going to get is 4 pi by C, 4 pi by C, and I will take typically J, I will assume to be will be constant over the surface, that's in region. So I will take J, so what I am going to have is S ds, and that side will be equal to B. Again, I am taking a thin region to be a constant, so let me line integral over dl. So fine, so now the ds is nothing but the area of this loop, that is L into L. So I can always replace this as your L, and dl is nothing but the total length of the loop. So now since your L is much larger than small l, so I can neglect this small l, so it become L, and this L plus L we are going to become as a 2L. So therefore this is going to be twice BL. So from here, and this 2 gets cancelled, become 2. So this gives me your J is equal to, this L also gets cancelled. So J is equal to BC divided by 2 pi L. And this is an interesting relation. It says my current density, the current density increases as the thickness of your reconnecting region becomes smaller and smaller. Fine. So let us try to go a step further. So we will try to see what is the energy released per unit volume. So though we have considered as a two-dimension here, we can assume the z-axis to be here and the configuration to be same all over the z-axis. So I can always consider a volume there. So let us try to calculate what is the energy released per unit volume due to the ohmic dissipation of energy. So we know that the ohmic dissipation of energy dE by dV is will be equal to, typically we know that sigma squared E. So now we know J equal to sigma E. So therefore this is, I can write it as your J squared by sigma. Fine. So J squared by sigma, and now I'm substituting this J here. I'm going to get this as your P square C square divided by 4 pi square L square and sigma. And again, let me write down this equation in the side. We need it. So dE by dV is equal to B square C square divided by 4 pi square L square sigma. And it says as my thickness of my neutral sheet decreases, so the energy dissipation will be much larger. So let this be 1. Oh no, I'll write it as 2. Let me have this J equation also. My J is equal to BC divided by 2 pi L, and this be 1. So we will be using these equations later. Fine. At the neutral sheet, your magnetic field is 0. So the pressure at the neutral sheet is purely your gas pressure. There is no magnetic pressure. Whereas an above and below, you have the magnetic field. The magnetic field pressure will be there, and the magnetic field pressure will be equal to, let me write it as P, that be equal to B squared divided by 8 pi. So this is the magnetic field pressure above and below, the outside the neutral sheet. Whereas at the neutral sheet, you are going to have only your gas pressure, because the magnetic field is 0. So under steady state, this magnetic pressure should be balanced by the gas pressure in the neutral sheet. So let us try to see that. So if we try to write the equation of motion in the neutral sheet, what you will get is rho into dV by dt will be equal to minus del px, because the pressure along the x-axis there you have. So, and del px by del x, because you only have the particle flow pressure goes from the x-axis. Fine. Well, so now we know your dV by dt is equal to del V by del T plus V dot del dot V. So now, since we are dealing with a steady state, the velocity won't change with time, so this becomes 0. So then I can, and this is the velocity motion is only along your x-axis, so this all becomes only derivative only in x. So we are going to have this equation will become, so this equation will become rho Vx del Vx by del x equal to minus, this should I write it as a Pg, this is the gas pressure. I will write as Pg, so this is minus del Pg by del x. Fine. So now, at x equal to 0, at this point, the velocity will be 0, and around that L, we will say around at the distance of L, we say the velocity is Vx. So when I try to integrate it over from 0 to L, what I am going to get is, this will be equal to half rho Vx square, because at 0, your velocity is 0, only at other side we have the velocity of Vx, and this will be typically equal to the pressure difference. So the pressure difference, I will write it as something like I will write it as del Pg. So now this pressure difference should be balanced by the magnetic pressure above and below the neutral sheet. So this should be equal to your B square divided by 8 pi. So this makes us 4. Therefore, this says your Vx is equal to B divided by square root of 4 pi rho, and this is nothing but Alfvén velocity, Alfvén speed, usually noted as Va. Fine. So it says the plasma comes out of this neutral sheet at the Alfvén speed. So we will note down this equation. So your Vx is equal to B divided by root of 4 pi rho, and which is nothing but your Alfvén speed. So now there's one more thing. The inflow should be balanced by the outflow. So that says so the inflow is V multiplied by the total length. You have the Z distance also. The Z will cancel from both the sides when you equate. So you will forget about the Z. So VL should be balanced by VXL. There are two surfaces. Of course, the two also will get cancelled from both the sides. So we can always write where VL should be balanced by Vx along the small l. So this gives me L is equal to VL by Vx, or that is equal to, since Vx is nothing but my L1 speed, so VL by VA. So let me write down this equation also. This is equation number 3, and we are having L equal to V capital L by VA. So this is your equation number 4. Fine.
Okay. Now the energy dissipated due to the ohmic process in the volume of the neutral sheet should be, rather the power dissipated in the neutral sheet should be equal to the magnetic energy convected into the neutral sheet from both the surfaces. Okay, and the ohmic power released per unit volume we have already derived. That's here. I made a mistake. You have to go back and correct. This is not energy. This is power. The power released per unit volume that we already derived here. So this should be balanced by the magnetic energy which is convected into the neutral sheet through the surface. So that is nothing but, so that means I should have my volume integral over dP by dV into dV should be equal to surface integral of the magnetic energy density is equal to B squared divided by 8 pi, and this multiplied by velocity and into ds. So they both should be balanced. So now we have this dP by dV already we calculated here. So that is equal to B square C square divided by 4 pi square L square and sigma, and this is the volume, integration of volume, and then this is nothing but my B square V by 8 pi and integration over the surface, that is ds. Now, okay, the volume we need the z dimension, but if you see, check the volume, so there's L into say some z value, and now the surface is nothing but L into that z value, so both the sides of z will cancel, so I can actually conveniently neglect the z, so the volume will be, so I can just write the volume as my L into L, so this makes it as L into L, and whereas here the surface is, these are two surfaces in the top as well as in the bottom, so this will be L into Z, and Z will cancel, so it remains only L, so and the other one L here, so it's going to become 2L, so 2L, and now this 2 gets cancelled and become 4 pi, this 4 cancels, so pi gets cancelled, and the L also goes off, so L square L, so from here B square cancels, so now I can always write my V, that's the velocity at which my magnetic lines are being convected into the neutral sheet. The V will be equal to, what's that we have? C square divided by pi L sigma. So this is the velocity at which the magnetic field is being convected into the neutral sheet. So now I can always, in the place of L, I can substitute this value. So that is going to become, so well, I don't want to put it here. So let me substitute that V. So what am I going to get is, so your L will be VA by VL. So this goes here. So this says your V square equal to C square VA divided by sigma. Well, this can be this can be conveniently expressed using the magnetic Reynolds number, which for the geometry what we have assumed can be written as. How do we get these values and all? You can, if you're more bothered about how do we get the values, you can actually go through the references given at the end of my lecture. So Rm, that is the magnetic Reynolds number, that is equal to 4 pi L VA into sigma by C square. So I can always express this guy in terms of this. So, and you can just substitute, you can see there are C square and the VA will become VA square and pi sigma L. These all are conveniently can be expressed in terms of magnetic Reynolds number. And when you do that, finally you will see your V will be 2 times the Alpha velocity into square root of your magnetic Reynolds number. And this is a very interesting expression. Velocity we got. So this is the velocity at which your magnetic field lines are basically convected into the neutral sheet. So this is what is going to decide your time scale during which your magnetic field lines are being convected. So now if you remember our earlier lecture, the earlier calculation, there also we calculated our the magnetic diffusive time scale that typically came as tau d. You can go back to the lecture and check it out. That is 4 pi sigma L square divided by C square. So I can always calculate a diffusive velocity. The velocity at which the magnetic field is diffused, that will become V of d will be equal to L divided by tau d. So that makes it as V of d will be equal to 4 pi sigma L divided by C square. So now you can see even this can be expressed in terms of your term of your magnetic Reynolds number, and then you will see when you substitute this, you will see the velocity at which the magnetic diffusion happens is something alpha velocity divided by Rn. Now, if you compare these two expressions, so I'm going to call this as A and this is B, you can see the velocity at which the magnetic field are convected into the neutral sheet are typically square root times the Reynolds number more than the diffusive velocity. And typically for solar flare, this Reynolds number is very high. So it says, since it's very high, the velocity at which the magnetic field lines are convected into is much higher than the diffusive velocity. So what the time scale we calculated earlier is not the right time scale. For example, typically for a solar flare, your magnetic Reynolds number can be typically equal to 10 to the power of 14. So in that case, so if you remember so that means your V will be typically 10 to the power of 7 times faster than your Vd. Or on the other hand, your time scale. If this is the velocity, I can always denote it with the time scale. Your tau, that's I call it as your reconnecting velocity time scale, should be typically 10 to the power of minus 7 times smaller than your diffusive time scale. And if you remember in our lecture, we found tau d, which comes something around 10 to the power of 7 years, and which was really alarming because solar fly happens in a few hours, and we were saying that something which was sorted out by Parker. So when you put back your reconnecting time scale, your tau r will be typically order of an year. Still, this is much higher because solar fly happens in a few hours. So still, this is much higher than the typically what's the time scale we observe for the solar flares. But yes, getting down from 10 to the power of 7 years to 1 year itself is a big achievement, which was basically goes to the Sweet and Parker model. So, and later on, Petschek model, you can get it from the references at the end of the lecture. The Petschek model, what he says, if there are standing shocks and the above and below the neutral sheets, this can reduce your reconnecting velocity much further. That way we can get a much shorter time scales. And further thing is, of course, the neutral sheet is not ideal neutral sheet like that, because a lot of plasma instabilities will be there along the sheets, and the sheets won't be actually a sheet. This would have been there's one particular instability called as a tear mode instability that tears off the sheets and makes into small pockets. But all these are, I will leave it to the advanced study. So if you are someone is interested in this, going into more detail of how this instability is going to affect your neutral sheet structure, or how the shock is going to modify your reconnecting velocity. So I advise you to go through the references given at the end of my lecture. And with this, we stop our lecture on reconnection, magnetic reconnection, how the particle being accelerated in the magnetic connection and all those things. And in the next series, we will go into the other interesting acceleration phenomena happening in astrophysics, that's the Fermi acceleration.